Okay, now I'm recording. Okay, this is problem 24, section 7.1. We had a building, and on top of the building was an antenna, 150-foot tall antenna. They want us to compute the height of the building. The angle of elevation from a person on the ground to the top of the antenna is 28.5 degrees. The angle of elevation from that same observer on the ground to the bottom of the antenna is 27.5 degrees. All right. So ladies, the key to this problem, if you want to make it a little more streamlined solution process as opposed to yesterday, which my method worked yesterday, my solution worked, but we would want to focus on this triangle here, this triangle right here on the top of this diagram here. And for the purposes of identification here, I'm going to call this angle here angle A. I have a question. What is the measure of angle A here? What would be the measure of this little angle here? If here to here is 28.5 degrees and here to here is 27.5 degrees, what does that leave this angle at being? Anybody? What would be the measure of this angle right here? This little angle. And we see that it would be 28.5 degrees minus 27.5 degrees, which would leave us with a what? 10-degree angle. Everybody see that? Okay. Another thing, ladies and gentlemen, we need to know the measure of angle B here. Well, the measure of angle B can easily be determined if we just use triangle ABC, the big triangle, A, B, well, the big triangle here. This angle A would be this angle here. This angle A prime, I'll call it, will just be this little 10-degree angle here. Okay. So to find the angle measure of angle B, we would use triangle ABC. We have a big old right triangle here, ABC. We know that this angle here, angle A, is 28.5 degrees. We know this is 90 degrees. So ladies and gentlemen, what does that leave angle B to be? How would we find angle B? Knowing that here to here, this angle A is 28.5 degrees, this is 90 degrees, how would we find angle B? Angle B would be 90 degrees minus 28.5 degrees plus 90 degrees, correct? Or it would just be 90 minus 28.5 degrees. So what does that leave us for angle B? What does that leave us? 90 minus 28.5. Is that, let's see, 61.5? Is that correct?
That's what I got.
Okay. So angle B here would be 61.5 degrees. Well, ladies and gentlemen, that's going to be angle B of the triangle that I extracted from the diagram here. Everybody see this here? I pulled out triangle A prime. A prime is this little angle here, which is 10 degrees. A prime BD. Everybody see the triangle I pulled out of the diagram there? We know this angle B now is 61.5 degrees. I'm going to label this side length here to be Y, of length Y. This side length is shared by both the small upper right triangle, small upper triangle, which is not a right triangle, excuse me, and it's shared by this lower right triangle here. Do we agree? Side Y is shared by this small little triangle that I extracted out of the diagram, and it's also shared by this right triangle right here. How can we find side Y from this small triangle that was extracted from the diagram? We don't know this angle here. This is not a 90-degree angle. We can't assume that. All right. In fact, it looks like an obtuse angle. This angle looks greater than 90 degrees. But ladies and gentlemen, to find the length of side Y, we can use the law of sines here. Everybody see this? The law of sines. So I can set up this proportion. I can say the sine of 10 degrees is to 150 feet, the height of the antenna, as the sine of 61.5 degrees is to side Y, which we don't know. So now we can solve for side Y. To do that, we cross multiply and equate to cross products, and then we'll divide both sides of the equation by the sine of 10. So this is going to be 150 feet times the sine of 61.5 degrees, and that'll be divided by the sine of 10 degrees. All right, get on your calculator and dial this up. Ladies and gentlemen, approximately what would be the length of side Y of this picture here? The length of side Y. We'll now know this length side Y here. So what is that length going to be on our calculator? We can round that off to, probably two significant figures. And make sure that your calculator is in, of course, degree mode. I'm getting like about 760 feet. Can anybody confirm that for Y?
I got that as well.
So now, ladies and gentlemen, we know Y. We know this side length here, Y, 760 feet. Well, not only is side Y shared by this upper triangle I pulled out of the picture, but it's also shared by this right triangle here. And ladies and gentlemen, one side of this right triangle here is the height of the building, H. Everybody see that there? So now we know Y is about 760 feet for this right triangle down here. This right triangle. And we know that this angle here, ladies and gentlemen, is 27.5 degrees of the right triangle, 27.5 degrees. So if I pull that right triangle out of the picture here, let me pull the triangle out of the picture so we can see what's going on. So now pulling that right triangle out of the picture, we know this is 27.5 degrees. We know side Y, we just found is 760 feet. How can we now find the height of the building? Everybody see that there? I pulled this lower right triangle out of my picture. Here it is. We found side Y to be 760 feet. We can now find the height of the building using a traditional trig function because we have a right triangle now. And so, ladies and gentlemen, to find the height of this building, we will take the sine of 27.5 degrees, and that's equal to the opposite side, which is the height of the building, over the hypotenuse, 760 feet. Now we can easily solve for the height of the building. The height of the building is nothing more than 760 feet times the sine of 27.5 degrees. Wait a minute here. Does that seem about right? We'll make sure we got everything right here. 10 degrees of that. Okay, let's see, what do we get when we do that here? So 60 times the sine of 27.5. Something still don't seem right. The sine 26.5. Something's still amiss here, ladies and gentlemen. That isn't right. The height of this building is about 3,500 feet. Went up with this triangle here. 150 feet.
Isn't angle A prime 1 supposed to be 1 degree, not 10? So you got 27.5 and 28.5.
1 degree. This is 1 degree. Yeah, there's my Monday mindset for me. That's a 1 degree angle. 28.5 minus 27.5 degrees is 1 degree. That's a 1 degree angle. So this is not correct. This should be the sine of 1 degree here. So Y should be 150 times the sine of 61.5 degrees divided by the sine of 1 degree here. All right, so what's that gonna be? 150 times the sine, 61.5 divided by the sine of 1 degree, which gives you like 7,553, about you want it to two significant figures, that would be about 7,600. 7,600 feet would be y. 7,600 feet would be y approximately. All right, and then the height of the building would be 7,600 feet times the sine of 27.5. 27.5, which gives us about, well, the height is approximately about 3,500 feet, just two significant figures. So that is the height of the building. Okay. So that's the idea behind doing the problem in a little bit more direct fashion, as opposed to what I did yesterday. Ladies and gentlemen. I mean, my solution did give us the correct answer in the end anyways yesterday, a little bit more drawn out algebraically though. But by using this triangle, this upper triangle here, and knowing this is 1 degree, 28.5 degrees minus 20.5, 27.5 degrees is 1 degree. Deducing this angle here, angle B is 61.5 degrees. We can then use the law of sines to find this missing side we call y here. Well, this side length y is shared by the upper triangle, but also shared by this lower right triangle. And then by knowing side y, which is 7,600 feet, and the angle of this right triangle down here, 27.5 degrees, and knowing that this is the side we want to find the height of the building, we can then use our traditional sine function, because we do have a right triangle now, and deduce the height of the building. So I just want to point that out, that that is the more direct way of maybe doing the problem. Okay. All right. Both methods work though. All right. This law of cosines, why do we need it? Ladies and gentlemen, why do we need the law of cosines? Well, I'll show you why. I'll give you an example. Law of cosines. If I have a triangle, suppose I have a triangle that looks like this, and we'll call it triangle ABC. All right. And of course, this is side, well, I'm not going to indicate any sides right now. All right, so suppose we have a triangle ABC. Notice it's not necessarily a right triangle. All right. Ladies and gentlemen, would the law of sines enable me to solve this triangle? If I knew, suppose that I knew this angle B, and if I knew the measure of angle C, and let's say that I knew the measure of side C, would that be enough information using the law of sines to solve this triangle ultimately? Yes or no? If I knew this information, angle C, B, and side C, could I use the law of sines? So the question is, would the law of sines solve this triangle? To solve the triangle means to find all three angles and all three side lengths. Would that work there? Anybody think that's enough information using the law of sines and or anything else we've learned in this course? This is all I know. Angle B, C, and side C. Do you think that would be enough information? Sean, do you think that'd be enough information to solve this triangle using the law of sines?
I don't think so.
You don't think so? The law of sines, what was the law of sines again? The sine of angle C, which I do know, would be to what side? Do I know a side opposite angle C? I do know the side length C. I would set that equal to what other ratio over here? I do know angle B. So I could say the sine of angle B is to side what? B. So could I find side B here? which is missing using the law of sines. Looks like we could what? We could solve for side B here. And then once we have side B, we got side C. We could easily deduce angle A's measurement, correct? We could then find what? Side A. Okay. By using the law of sines again. We could say like the sine of angle C is to side C, as the sine of angle A is to side A. So yes, ladies and gentlemen, we could solve this triangle if we just knew angles B, C, and side C using the law of sines. The law of sines would work there. Okay. Now, I have another question. Suppose we have this triangle. Again, we'll call it triangle ABC. All right, suppose, ladies and gentlemen, I tell you in this triangle, we want to solve this triangle. Suppose in this triangle that we know side B, excuse me, side A, we know side B, and we know angle C. So, ladies and gentlemen, we know side B, we know side A, and we know angle C. Could the law of sines help us solve this triangle? Anybody want to weigh in on this? You think the law of sines will help us solve this triangle here if we know side A's length, side B's length, and angle C? We don't know angle B, and we don't know angle A, and we don't know the length of side C. Ladies and gentlemen, do you think the law of sines would work here? Anybody want to take a stab at this?
No, it wouldn't.
It's not going to work. It's not going to work, ladies and gentlemen, because we have a problem here. You see, we know side A's length, but we don't know angle A. We know side B's length, but we don't know angle B. We know angle C, but we don't know side C. So you cannot set up a proportion using the law of sines to find, let's say, side C. I mean, you know angle C, so you can say the sine of angle C is to side C, which we don't know. But then you'd have to have something over here. You'd have to have something like the sine of angle A or B, but we don't know what angle A or B are, regardless of knowing, you know, the length of side A or B. You see, we got a big problem here. I mean, we don't have enough information here using the law of sines to solve this triangle. The sine of angle C, we do know, would be over some unknown length side C. But the problem is we don't know angle A or B's measure, so we cannot set up a proportion involving the law of sines to solve this triangle. Ladies and gentlemen, this is called the side angle side scenario with a triangle. We know a side, an angle, and we know another side. So we know two sides and an included angle in between the sides. The law of sines will not solve a triangle that is side angle side, where we know a side, an angle, and a side. Law of sines fails. Doesn't work. So how are we going to solve this triangle? There's got to be a way. How are we going to do it? The law of sines fails for side angle side. Ladies and gentlemen, here's another scenario here. Suppose I have a triangle. Triangle ABC. Suppose that I indicate to you that we know side C, we know side A, and we know side B. Will the law of sines help us here? Anybody? Will the law of sines help us to solve this triangle if we know all three side lengths? Do you think the law of sines will help here?
we don't know the angles, so.
We don't know any angles. You're correct. We don't know any one of these angles. Ladies and gentlemen, there's no ways in the law of sines we can set up any proportion to solve for any one of these angles. The law of sines fails here. This is a scenario where we know all three sides of a triangle, side, side, side. If we know side, side, side. If we know all three sides of a triangle, the law of sines does not help us solve the triangle. It fails. So the law of sines works okay for triangles just so long as we don't have the side angle side or the side, side, side scenario. But what if we have the side angle side or side, side, side scenario? What are we going to do then? How are we going to solve the triangle? How are we going to crack the ice and find one of these angles here? Well, ladies, on to the rescue is the last law we'll look at in this course. It's called the law of cosines. The law of cosines will solve those triangles that were mentioned before, the side angle, side, 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 side. So the law of cosines. I would like to derive this law for you quickly here. It don't take too long in its derivation. I just want you to kind of appreciate where the law comes from. So I will walk through the derivation, just like I did for the law of sines. Okay. Here we have a triangle, A, B, C. This is not necessarily a right triangle. Notice there's no right angle symbol in here. It's just some triangle. Just like yesterday, ladies and gentlemen, I'm going to pick an angle and drop a perpendicular from that angle down to the opposite side, called an altitude or a height. Everybody see that there? We'll call this H for height or altitude. Same thing I did yesterday with the triangle ABC. We know this side here, opposite angle B, is side of length B. This side, opposite angle A, is side of length A. We'll call this vertex point here, we'll call it D. We'll call the length of this little right triangle here, ADC, we'll call it X. Ladies and gentlemen, what then will be the length of this side of the right triangle, BDC? Anybody? What would be an expression to represent this length here, DB? For a right triangle, BDC. What could I use here? Remember, what side do we label opposite angle C? It's side of what length? In other words, what is this entire length here? Opposite angle C is side of length C. So later on, what would be the length of DB here? Anybody? If this is here, AB is C units in length, AD is X units in length, what would be the length of DB? What do you think? What do you think, Bailey? If from here to here is C units in length, this is X units in length, what do you think this length would be here, DB? C minus what?
C minus X.
C minus X. Everybody see that there? That true? Does this diagram make sense to you so far, ladies and gentlemen?
Yeah.
Okay. Now, using triangle BDC, the right triangle BDC. Everybody see the right triangle on the right side of this picture here? And the Pythagorean theorem. Okay, and the Pythagorean theorem. Using triangle BDC, do you agree I can take the length of its hypotenuse, which is A squared, and set that equal to the sum of the squares of the legs? That's to say equal to H squared plus C minus X squared. Do we buy that? for triangle for triangle BDC. Expanding this out, c minus x times itself, just foiling that out. We'll have a squared plus c squared minus 2cx plus x squared. After multiplying this out. We'll have a squared is equal to c squared minus 2cx plus h squared plus x squared, just rearranging a couple terms. Do we understand what's going on so far here, Liz? Okay. Now, turning our attention and using triangle ADC. You see the right triangle? ADC. Using the left-right triangle now. Using the left-right triangle. And the Pythagorean theorem. There's on PT, short for Pythagorean theorem. You agree, using triangle ADC, I can say its hypotenuse length, which is b units, so b squared is equal to what? X squared plus h squared? Do we agree? But ladies and gentlemen, another name for x squared plus h squared is b squared. So do you agree that this b squared here, which is x squared plus h squared, can come up here and take the place of what quantity in this equation? It can take the place of h squared plus x squared. Everybody see that here? Everybody see that there? Another name for h squared plus x squared is b squared. So therefore, this equation, after making that substitution, this equation now is going to look like this. A squared is equal to c squared minus 2cx plus what? What goes in place of this? B squared. Furthermore, ladies and gentlemen, using triangle ADC, the right triangle on the left side of this picture, ADC. If I take the cosine of angle A here, do we agree that the cosine of angle A is the adjacent side over the hypotenuse? So it would be x over b. Whereby when we solve this equation for b, or for x rather, we multiply both sides by b. So x is equal to b times the cosine of A. Do you agree? Using the right triangle on the left side of this picture here, cosine of angle A right here is x divided by b, adjacent over hypotenuse. But ladies and gentlemen, another name for x is b times cosine A. So b times cosine A, another name for x, can come down here into this equation and take its place for x right there. Everybody see that there? Another name for x is b times cosine A. Therefore, this equation, after making a substitution now, can be refined and written this way. A squared is equal to b squared plus c squared minus 2. What's x? What's another name for x? B cosine A. So b times c. And then we got the cosine of A. Ladies and gentlemen, you are looking at one of three forms for what's called the law of cosines. Right there. That's one of three forms of the law of cosines. Side A squared equals side B squared plus side C squared minus 2 times the length of side B times the length of side C times the cosine of angle A. That's called the law of cosines. And by going through a similar argument, by dropping a perpendicular altitude from any one of these other angles, angle B to this side or angle A to this side, you could hammer out two other equivalent forms for the law of cosines. Any questions on the derivation here, which is also in your textbooks for your viewing? The derivation of one form of the law of cosines here. Was it logical the way it was derived? Makes sense? Okay. All right, so now, ladies and gentlemen, I can just lay it out for you. So, law of cosines. Given any triangle ABC, ladies and gentlemen, where the triangle is not necessarily a right triangle, you have these three forms for the law of cosines. We just showed you one. A squared is equal to B squared plus C squared minus 2 times B times C times the cosine of angle A. That's one form. Suppose we have the law of cosine solved for side B. So B squared is equal to A squared plus C squared minus 2 times side A times side C times the cosine of angle B. Or C squared, side C squared is equal to side B squared plus side, well, actually, normally they have this, hold on a second, they normally have that spun around, they call that A, if you want to put them in alphabetical order, left to right. So, ladies and gentlemen, you are looking at the three forms for the law of cosines here. Everybody see this here? These are called the law of cosines. Now, there is a distinct way of remembering these. You can see there's an obvious pattern here. Whatever side is on the left side of the equation, that is also corresponds to the angle on the right side, which is the argument of the cosine function. Side A, angle A. Side B, angle B. Side C, angle C. Notice that. Notice, ladies and gentlemen, whatever side is on the left side of the equation, that means the other two sides are on the right side of the equation. So side A is on the left, so that means that leaves side B and C to constitute the right side here, B and C. Side B is on the left side, that leaves sides A and C to take up the slack on the right side. Side C is on the left side, sides A and B take up the slack on the right side. Everybody see that there? These are three equivalent forms of the law of cosines for any triangle ABC. These these laws of cosines, ladies and gentlemen, will solve the case where you have three known sides of a triangle and or you have a side angle side known of a triangle that the law of sines would fail on. So this is called the law of cosines here. Okay. All right. Well, any questions about the law of cosines here? See if we can apply that to maybe a couple problems here. So let's go to section 7.3. Okay. Section 7.3, law of cosines. Let's go down and see if we can maybe do a problem. Here's an interesting note, ladies and gentlemen, in passing, involving the law of sines and cosines. When you are given three sides of a triangle, in other words, if we just know the three sides of a triangle, we don't know any of the angles of a triangle. You want to remember this. You want to always use the law of cosines to find the largest angle opposite the largest side. So if you just know three sides of a triangle and you want to try to solve the triangle, you want to use the law of cosines to crack the ice to find the largest angle opposite the largest side. Then proceed onward by using the law of sines then to find the smallest angle opposite the smallest side. Okay. By that way, you can avoid any pitfall involving what's known as an ambiguous case. Okay. All right. So let's just try to dive into a problem here and see how we can apply the law of cosines. Problem number 2. This occurs on page 351. Page 351, number 2. They indicate to us that we have a triangle ABC. Side A measures 100 inches. Side B measures 60 inches. And angle C, notice, is an obtuse angle, which is 120 degrees. So for that reason, we have an obtuse triangle here, ladies and gentlemen. We do not have a right triangle. Okay. I'm just drawing a picture here, and I'm going to start labeling the things we know. We know the side A is 100 inches, and side B is 60 inches. And they want you to find side C. Okay. All right. I have a question for you, ladies and gentlemen. Could we, in order to find side C, could we use the law of sines? Would the law of sines work here? Yes or no?
No,
The law of sines will not work here. It's not going to work because we don't know, although we know, side lengths B and A, we don't know angles A or B. We don't know them. So you can, even though you know angle C, you don't know side C, you cannot set up a proportion using the law of sines to solve for, any one of these other things here. I mean, you could start by saying the sine of angle C, which is 120 degrees, is the side C. Nothing wrong with that. That's cool. But what are you going to have over here? The side of angle A or B, ladies and gentlemen, we don't know angles A or B. Is the side A or B? See, we got a big problem here. Although we know sides A and B's lengths, we don't know any angle A or B. So you cannot complete this with the proportion using the law of sines. Doesn't work. Got to use the law of cosines. And ladies and gentlemen, I have a question for you. If we want to find side C, what would be the relevant version of our law of cosines we'd want to work? The first, second, or third formula. What do you think? First, second, or third formula will work in the context of our situation here. Anybody?
The third one.
Yeah, the third one enables us. Notice it's already solved for C. Well, not exactly. We have to take the square root of both sides, but this used the third version of the law of cosine. So therefore, we'll follow along. So in for A, we drop to 100 inches. In for B, we drop in 60 inches. For angle C, we drop in 120 degrees. So let's set up the third equation for the law of cosine. So side C squared is equal to side A squared, which is to say 100 inches squared, plus side B, which is 60 inches squared, minus 2 times side A, which is 100 inches, times side B, which is 60 inches, times the cosine of angle C, which is 120 degrees. You see, the law of cosines is going to crack the ice for us and enable us to find the length of side C. Then we'll be in business. To find side C, of course, we're going to have to hit both sides of the square root function. So side C is equal to the positive square root of all of this. And what I would like you to do, ladies and gentlemen, is get on your calculator. And I would like you to dial this up on your machine. Go ahead and tell me to, it looks like, we'll take it out to 2 significant figures, what the length of side C would be here, okay? So get on your calculator and dial that up, ladies and gentlemen, you'll have the length of side C. Let me know if anybody gets an answer. I'm obviously not having a good day. I can't do subtraction today. So please, somebody else work this out so we can compare answers. Make sure you're in degree mode. Let me know if anybody got anything. I'm getting about 140 inches. Anybody get that? Anybody confirm that? About 140 inches. Anybody out there get that?
Hang on, Mr. O, I'm still working. I accidentally didn't have it in degrees, so I'm doing it again.
Actually, that's exact. That's not even approximate. That gives you an exact. I didn't have to round off there. Yeah. If you can get 140.
I got 142.
Okay, 140 inches for side C. Just make sure that, you can do this calculation. It looks like, pretty stiff calculation here. So just make sure you can crank it out. Well, ladies and gentlemen, I have a question for you. I know your author doesn't ask you this question with this problem number 2. All they wanted is side C. We're done with this problem. But what if I want to go further with this problem? What if I also wanted to find angle B? Do we now have enough information to use the law of sines to find missing angle B? Or do we have to use the law of cosines again? What do you think? Do you think the law of sines, because the law of sines is simpler than the law of cosines. So if you can use the law of sines, use the law of sines. You think the law of sines will take us the rest of the way in finding angle B? Now knowing side C? Anybody think it'll work? Help me set up a proportion to find side B using the law of sines to find angle B. Help me set up a proportion to find angle B using the law of sines. I can say the sine of what? Angle B is to what side? Sine of angle B is to what side? Side B. 60 inches. As the sine of angle C, which is 120 degrees, is now to side C, which is 140 inches. Now we can use the law of sines to find angle B. Cross multiplying, equating the cross products. Dividing by 140 inches, both sides of our equation will have the sine of angle B is equal to 60 inches times the sine of 120 degrees divided by 140 inches. To find the angle B here, we take the inverse sine of both sides of this equation. So we take the inverse sine of 60 times the sine of 120 degrees divided by 140. And approximately, what does that give us for an angle, for angle B? So now we can use the law of sines to find angle B. So we take the inverse sine of 60 times the sine of 120 divided by 140. And ladies and gentlemen, to two significant figures, I'm getting about 22 degrees. About 22 degrees for angle B. And then angle A could easily be found by subtracting from 180 degrees, 120 plus 22 degrees. See how we solved that triangle there? So to solve the triangle, we had to crack the ice by using the law of cosines to find side C. Law of sines would not work. Once we found side C, we could then find the measure of angle A or B. It suggested that the smaller angle is to be found using the law of sines. Remember that yellow shaded box? We should find the smaller angle using the law of sines once we find side C using the law of cosines. That's why I opted to find angle B first, which is 22 degrees. Then angle A here would be 180 degrees minus 142 degrees. And 180 minus 42 degrees would be what? 38 degrees. Did I get that subtraction correct? Did I redeem myself this morning? Would that be the measure of angle A? 38 degrees. 180 degrees minus 142 degrees, I believe, is 38 degrees. Is that correct? I believe I have that correct. You see how we solve that triangle, ladies and gentlemen, first by using the law of cosines and the law of sines? Any questions about number 2 there? Again, all they wanted for number 2 is they just wanted you to find side C. I wanted to go a little bit further. I want to show you how then we could then use the law of sines to find like one of the other acute angles, angle B. And then everything else falls in our lap and we're done with that problem. We've solved the triangle. Okay. Any questions with how we proceeded with that problem number 2? Ladies and gentlemen, what if we only know 3 sides of the triangle? And they want us to solve the triangle, like number 12 here. They give us a triangle, ABC, of which they tell us side A, B, and C's lengths respectively are 5, 10, and 12 inches. They want us to find the 3 angles of this triangle. They want us to solve this triangle here. So I will draw a triangle on my paper, label its vertices. This is problem number 12. Side A is to be 5 inches. Side A is to be 5 inches. Side B is to be 10 inches. And they want us to solve this triangle. In other words, notice it says solve for the largest angle first and round to the nearest 1/10 of a degree. So ladies and gentlemen, I have a question for you. What angle are we going to solve for first based on the instructions? Angle A, B, or C? Which side angle first? This is a side scenario. We know where we know all 3 sides of the triangle, and yet we know none of the angles. The law of sines fails here. We have to use a law of cosines to break the ice. Ladies and gentlemen, what angle do we solve for first? Anybody?
C.
C. The longest side is side C, so that must be the largest angular measurement is angle C of the 3 angles. So to solve for angle C, solving for angle C using law of cosines. We use which version? We use this one. C squared is equal to A squared plus B squared minus 2 times B times C times the cosine of the angle we want to try to find, which is angle C. I see that there? We have to solve for angle C. And so, ladies and gentlemen, what we got to do is move everything over to the left side and try to isolate angle C on one side of our equation. To do that, we subtract A squared and B squared from both sides first. So therefore, we have side C squared minus side A squared minus side B squared is equal to negative 2BC times the cosine of angle C. Divide both sides of our equation by negative 2BC. This all cancels, and we're left with this now. The cosine of angle C is therefore equal to side C squared minus sides A squared minus side B squared divided by negative 2 times side B times side C. Something's not right with my formula, ladies and gentlemen. What's wrong with this formula here? There's an error here. This isn't one of our law of cosines here. What's wrong with this formula here, ladies and gentlemen? There's a mistake.
Should it be 2 times BA?
Right here, this is not right. Look at, this is the one we're trying to tap into. Do you agree? See that there? This is the one we should be using. It should be minus 2 times AB. All right, that's not correct. This should be AB. All right. All right. So no good. So ladies and gentlemen, we're not using the correct formula. C squared is equal to, here we go, A squared plus B squared minus 2AB, there we go, times the cosine of angle C. Make sure you get these formulas down correctly. Therefore, we have C squared minus A squared minus B squared is equal to negative 2AB times the cosine of angle C. Now we divide both sides by negative 2AB. These cancel. All right, so therefore, the cosine of angle C is equal to C squared minus A squared minus B squared divided by negative 2AB. And to round things out, then, ladies and gentlemen, to find angle C, then we're going to have to take the inverse cosine of both sides of this equation. So angle C, in essence, is going to be the inverse cosine of C squared minus A squared minus B squared divided by negative 2AB. Then we'll have our answer. Everybody see that there? That's how we're going to find side C, or angle C, excuse me, for this triangle. So we got to drop in what we know into this formula. So angle C is equal to the inverse cosine of side C squared, which is to say 12 squared. I'm going to leave the inches out. We know it's inches. Minus A squared, which is minus 5 squared, minus B squared, which is 10 inches squared. And that's divided by negative 2 times 5 times 10. So approximately, ladies and gentlemen, what would be the measure of angle C then? Make sure we can do this on our calculator, this calculation. So take the inverse cosine. This is not an elementary calculation, so make sure that you're able to do this on your machine, ladies and gentlemen. You may have to use some parentheses, okay? Make sure you're all able to do this. Let me know if anybody gets an answer. I'm serious. Don't just, look at this and think that, yeah, I can do that. No, actually convince yourself. If you got your calculator handy, ladies and gentlemen, dial that in. See if you get the correct answer here. There's a many different ways of messing this up and getting something that you should not be getting. Okay. So I would strongly recommend you enclose the entire numerator inside parentheses here and the entire denominator to avoid a logical error. Anybody get it? I'm getting about to the nearest 10th of a degree. I think they wanted a 10th of a degree. Is that correct? I'm getting about 101.0 degrees. Anybody get that? About 101.0 degrees for angle C. Anybody get that? Let me know if anybody gets that. The inverse cosine of 12 squared minus 5 squared minus 10 squared, all divided by negative 2 times 5 times 10.
Mr. O,
Yes,
I got 100.95.
100.95, so about 101 degrees. Is that correct?
I guess so, yeah.
Does that seem about right for angle C? That it would be obtuse?
Yeah.
It makes sense just by looking at the picture here. I mean, side C is the longest of the three sides. So it seems like this would have to be an obtuse angle. It kind of looks that way, but 101 degrees. Ladies and gentlemen, now that we use the law of cosines to find the missing angle C, we then could find one of our other two angles, A or B. Anybody remember which one we should find in using the law of sines according to what I showed you in that yellow shaded box? What was the recommendation, ladies and gentlemen? What angle would you now want to use the law of sines to find angle A or B? Anybody remember that little recommendation?
B.
Yes. Notice, ladies and gentlemen, the recommendation in that yellow shaded box says that when you want to crack the ice, if you know just three sides of a triangle, you want to first find the largest angle of that triangle by using the law of cosines. Then, using the law of sines, you want to find the smallest angle that remains, the smallest of the other two angles. And that would be angle B, because its side length is side of length 10, which, wait a minute. Side B has a length of 10 inches, side A has a length of 5 inches. Which angle should we be finding, A or B, ladies and gentlemen, if we want to find the smaller angle using the law of sines now? We should be finding not angle B, right? But what? Angle A.
A.
Angle A. So we should be finding the angle of A now using the law of sines. So let's set up a ratio or proportion to do that. So we'll say the sine of angle A is to side A, which is 5 inches, as the sine of angle C, which now we know is 101 degrees, is to side C, which is 12 inches. Now we can find sine, angle A. Cross multiplying, equating the cross products, taking the inverse sine of both sides of the equation, ladies and gentlemen. To make a long story short, angle A will be equal to the inverse sine of 5 times the sine of 101 divided by 12. So angle A will be equal to the inverse sine of 5 times the sine of 101 divided by 12. Let's dial up on our calculator and see what we get. So the inverse sine of, and again, I would include this entire numerator inside parentheses to avoid a logical error on your calculator. So 5 times the sine of 101 divided by 12. I'm getting about 24 degrees. Can anybody confirm that? Angle A is about 24 degrees. And now that we know angle A, angle B falls into our lap, because angle B will just be 180 degrees minus 101 plus 24 degrees, correct? And we have solved that triangle. So to crack the ice, first, knowing all three sides, we had to find the the largest angle, missing angle, which was angle C, using the law of cosines. Once we found angle C, we then turned it over to the law of sines and finding the smaller of the two angles, A or B, we found angle A. And once we know angle A and C, obviously angle B drops into your lap, just being the difference of 180 in the sum of angle A and C. Okay. All right. Do we see how the law of cosines is getting us out of hot water with either a side or a side angle side scenario? Where the law of sines fails, ladies and gentlemen, you have to use the law of cosines. Any questions, remaining questions on problem number 12 here? One where we know all three sides of a triangle. Application problems. There's several in here. I wanted to do maybe one or two here, ladies and gentlemen. Number 28, distance between two ships. Two ships leave the harbor at the same time. The first ship is traveling at 14 miles per hour on a course with a bearing of 13 degrees west of south, while the other is traveling at 12 miles per hour on a course with a bearing of 75 degrees east of north. How far apart are the ships after 3 hours? Assuming these ships do not speed up or slow down, but maintain a constant speed. And that's the key assumption in this problem. Because, ladies and gentlemen, if these ships are constantly changing speed through time, then you would have to use what's called integral calculus to deal with the problem. Algebra and trigonometry fall apart. The calculus was ideally suited and designed to deal with situations where variables are constantly changing through time. That's the power of the differential and integral calculus. Okay. Number 28, two ships leave a harbor at the same time. The first ship's traveling 14 miles per hour on a course of 13 degrees west of south. Let's try to envision that, west of south. So it's heading in a southwest direction. So I'm going to have a ship right here, ladies and gentlemen, on my paper. I'm going to put a little point or a little dot on my paper. This is the ship, and it's heading on a bearing or a heading of 13 degrees west of south. we put a little north-south line through this ship's location. There's north, there's south. It's got to be 13 degrees west of south. 13 degrees west of south, ladies and gentlemen. This is west, this is east. 13 degrees west of south, we'll have the ship going off in this direction right here. Do you agree? The first ship is going on a heading of 13 degrees west of south. This angle here is 13 degrees. They tell us that. 13-degree angle. Do you agree? 13 degrees west of south. It's going at what speed? 14 miles per hour. For how many hours? 3 hours. Ladies and gentlemen, what distance does a ship travel? Traveling at a speed of 14 miles per hour for 3 hours. Distance equals rate times time. Distance is equal to 14 miles per hour times 3 hours. Notice the hour units cross cancel out, leaving you with miles, proper units for distance. Notice how the units work here. 3 times 14 is 42. 42 miles. This ship heading at 13 degrees west of south will have traveled 42 miles from the harbor where it left. So this is 42 miles, that length there. The length of this vector, ladies and gentlemen, we call this a vector, is 42 miles. Okay. Let's read on with this problem here. That's the first ship. But it says there's another ship traveling 12 miles per hour on a course with a bearing of 75 degrees east of north. Ladies and gentlemen, it leaves the same harbor at the same time, traveling 75 degrees east of north. Here's the harbor where the first ship left. The second ship also is going to leave this same point here at the same time, 75 degrees east of north. There's your north-south line through the second ship. 75 degrees east of north is going to have that, ladies and gentlemen, looking like this. There's the vector or the heading for the second ship. 75 degrees east of north. That would be that angle there. Do we understand this picture so far? That's for the second ship. 75 degrees east of north is its heading. It's heading in a east-northeast direction. The first ship's heading kind of like in a south-southwest direction. The second ship travels at a speed of, what was its speed? Was it 13 miles per hour? 12 miles per hour, excuse me, for 3 hours. Ladies and gentlemen, how far did the second ship travel from harbor? 12 miles per hour times 3 hours is 36 miles. They want to know after 3 hours, what would be the distance between these ships? They want to know the length of this side of our triangle, ladies and gentlemen. We'll call it D for distance. They want to know the distance between these ships 3 hours after they leave the harbor at the same time, traveling at their respective speeds and their respective headings. Ladies and gentlemen, how are we going to find this distance of this triangle we created here? Well, first of all, it would be great if I could find this angle here. Anybody know how we can find this angle here, ladies and gentlemen? We know here to here is 13 degrees. That's your 13 degrees west of south heading for the first ship. We know this is 75 degrees east of north. We know this angle is 75 degrees. How can I use those angles to deduce this angle here of this triangle? How can I deduce this angle here? Anybody? Do we got enough information to deduce this angle or not? Or are we screwed?
Add those up and subtract them from 180.
Okay, so we can add these together, right? And subtract from 180 here. All right. Suppose we can't really see that. I don't know. I mean, I'll tell you what. What does this angle have to be right here? I'll give you a hint. What does this angle have to be right here, ladies and gentlemen? That's 90 degrees, isn't it? The angle between south and east. What does this little angle have to be right here, ladies and gentlemen? This little angle here. Well, we know from north to east is 90 degrees. We know this is 75 degrees. Do you read this little angle here then would have to be what? 90 degrees minus 75 degrees. This angle here would be 90 minus 75 degrees, which would give you how many degrees? 15 degrees. So this is 15 degrees here. So this angle here to here is 15 degrees. So ladies and gentlemen, look at, if we want to find this angle here, this big old angle here, here to here, we know this is 13 degrees. We know this is 90 degrees. We know this is what? 15 degrees. That should take care of it, correct? 13 degrees plus 90 degrees plus 15 degrees would give us this angle here to here. So what angle is that? I call this distance D here. If that's distance D, maybe we'll call this angle D here, this big old angle here, D. So angle D here would be, what did I say? It was 13 degrees plus 90 degrees plus 15 degrees. Plus 90 degrees plus 15 degrees. And that would give us 105, let's see, what's that, 28? Be 100 and what, 18 degrees, is that correct? Or did I mess that up? 118 degree angle. So ladies and gentlemen, this angle is 118 degrees. All right, so therefore, pulling that triangle out of all the mess there, what we've accomplished here, we have a triangle here now. We know this is 118 degrees. We want to find this side length here. We know this is 42 miles. We know this is 36 miles. And we call this angle D. So ladies and gentlemen, the law of cosines, do you agree? Would enable us to find the distance between these ships here. We have a side angle side scenario. Notice side angle side. We know two sides and an included angle sandwiched in between the sides. So to find side D here, which maybe I could have called it, side C for the notational purposes of the law of cosines. So to find side C here, we would say C squared is equal to A squared plus B squared minus 2AB times the cosine of angle C. All right, so here's your law of cosines. Side C is the square root then of A squared plus B squared minus 2AB times the cosine of angle C. So side C, which is the distance between the ships after 3 hours, is going to be side A's length, which it doesn't matter which one you call side A and B here. 42 miles squared plus 36 miles squared minus 2 times 42 times 36 times the cosine of 118 degrees. Get on your calculator, ladies and gentlemen, and dial that up. And approximately what is the distance between those ships 3 hours after they leave the harbor at the same time, traveling their speeds on their respective headings. So let's see if we can do this. Just make sure that, you're able to crank these out here. I don't know if you have access to a calculator right now or not, but just make sure that, you're able to do these calculations. To the nearest whole mile, what are we getting about? I'm getting about 67 miles. Can anybody confirm that? The distance between those ships after 3 hours is about 67 miles. They're 67 miles apart. Can anybody confirm that?
I got that as well.
About 67 miles apart. Ladies and gentlemen, see how the law Anybody else get that?
So yeah, 66.9, yeah, 67.
Oh, we're close 67. Oh, 67 miles apart. See how the law of cosines can help us with an application problem. All right, there's one more application problem I would like to show you. The true course and speed of an airplane. A plane is number 30. A plane is flying with an airspeed of 240 miles per hour with a heading of 273 degrees. The wind currents are running at a constant 46 mile per hour in a direction of 262 degrees. Find the ground speed and true course of the true course of the plane. Ladies and gentlemen, you take an airplane up, you're oftentimes fighting a wind, whether it's a headwind, a tailwind, or a crosswind, or some sort of a wind that's striking your aircraft at an angle. That's going to change your heading relative to the ground, somebody fixed on the ground. Ladies and gentlemen, we got an airplane that's heading 273 degrees. You know, in aeronautical circles, ladies and gentlemen, north is called 0 degrees. Easterly direction is called 90 degrees. If an aircraft is on a heading of 090 degrees, ladies and gentlemen, they're heading in an easterly direction. If an aircraft is on a heading of 180 degrees, ladies and gentlemen, they're on a heading south. If an aircraft is heading 270 degrees, they're heading in a westerly direction. That's the way it works in aeronautical circles, okay? So 0 degrees is north, 90 degrees is east, 180 degrees is south, 270 degrees is west. I know that's all turned around from our XY plane, but this is the way it is in aeronautics. All right. So an aircraft is heading on heading of 273 degrees. So an aircraft, ladies and gentlemen, is heading this away. It's on a heading of 273 degrees. So this angle here is 273 degrees. They tell us that. And the wind, however, is blowing at 262 degrees, 262 degrees. So, ladies and gentlemen, the wind is blowing at 262 degrees. So this angle here to here, ladies and gentlemen, is 262 degrees. Wait a minute. 273 degrees is from north. I'm sorry, from north. So this angle is also from north. There you go. 262 degrees, 273 degrees. So this is the wind. This is the airplane. The airplane is right here. Okay, it's flying in a northwesterly direction, but it's fighting, ladies and gentlemen, a northeast wind. It's fighting a northeast wind. Now, these are called vectors. And the beautiful thing about vectors, ladies and gentlemen, you'll discover if you get into physics, is you can always pick a vector up and move it anywhere in the XY plane, anywhere, as long as you preserve its direction, you don't change its direction, and you don't change its speed, the length of the arrow. The magnitude of the vector is the length of the arrow, or speed. So I could pick this vector up, this wind vector up here, and I could move it so that it's up here now. Still has to be the same direction, ladies and gentlemen, so we can't change the direction, we cannot change the length. And by doing this, ladies and gentlemen, by moving this wind vector up here, we create a parallelogram here. Everybody see the parallelogram I created? Okay, it's supposed to be a parallelogram. The resultant vector of this aircraft, ladies and gentlemen, this aircraft is moving in a northwesterly direction, but the wind is coming from the northeast, pushing the aircraft in a true heading that is going to be more west of north. This will be the resultant vector of the aircraft right here. The aircraft's resultant vector will be this vector here. So notice the wind, see the aircraft is wanting to go in a northwest direction, but the wind is pushing it to the southwest. So the true heading of the aircraft, ladies and gentlemen, is more west of north, because this is the wind and this is the plane's vector. Plane's vector, wind's vector. The wind is pushing it more to the south and west. Do you agree? This is the resultant vector here. The resultant vector in which the plane is actually heading relative to the ground due to the wind pushing it off course. Okay. So in reality, a plane will actually be following this resultant vector direction. The plane wants to go in the northwest direction, but the wind is pushing it. Do you agree? Pushing it more to the south and west. Do we understand this picture as to what's going on here a little bit? Does it make any sense, ladies and gentlemen, how the wind is deflecting the plane's path? The plane wants to go in the northwest direction, but the wind is pushing it more to the south and west, so that the actual true heading of the airplane is more west of north. Okay, more west rather than north. All right. All right. Now we're running low on time here, but this is C here. Plane is traveling 240 miles per hour and the wind is 46 miles per hour. So the airplane is 246 miles per hour and the wind speed is 46 miles per hour. So we can label the sides of this triangle with these speeds here. And what they want here, ladies and gentlemen, is they want us to try to find the what? What do they want us to find here? Find the ground speed, the speed of the plane relative to a person fixed on the ground. So they want us to find the speed of this airplane as it would be on the ground here. And how are we going to do that? Well, how are we going to do that there? Well, ladies and gentlemen, do we agree from here to here is 273 degrees and from here to here is 262 degrees? So I claim we can find this angle of our parallelogram by subtracting 262 degrees from 273 degrees. And 273 degrees minus 262 degrees, wait a minute, don't tell me, is 11 degrees. Did I get that correct? Or did I botch that one? 273 minus 262 is 11 degrees, correct? Well, that must be this angle of our parallelogram over here, 11 degrees. But ladies and gentlemen, parallelograms, angles must add up to 360 degrees. And these angles must be of equal measurement here. This angle here must be the same as this angle here. So to find one of these angles, ladies and gentlemen, all we have to do is take 11 degrees and add it to 11 degrees. That gives us 11 degrees plus 11 degrees is 22 degrees. But the sum of all four angles of the parallelogram must be 360 degrees. So we'll take 360 degrees and subtract off 22 degrees. What does that give you? 360 minus 22. Is that 338 degrees? And then, ladies and gentlemen, we'll divide 338 degrees by 2. Because these angles must be the same measure. So they're both of the same measure. Do I have my math right here, ladies and gentlemen? So, ladies and gentlemen, after doing that, we deduce then that this angle must be 169 degrees here. Pulling that triangle out of our picture now. We now have this triangle, 169 degrees. We know this is 46 miles per hour. And we know this is 246 miles per hour. Using the law of cosine, ladies and gentlemen, we can then find the true ground speed of the airplane, the speed of the airplane relative to somebody fixed on the ground looking up at the airplane. And this is due to the wind deflecting the airplane. So we can find the speed here. And so using the law of cosines, side C is equal to the square root of 46 squared plus 246 squared minus 2 times 46 times 240 times 46 times 246 times the cosine of the angle 169 degrees we deduced. Law of cosines will give you the true the speed of the airplane was 240 miles per hour. 240 miles per hour. So this will be 240. 240, ladies and gentlemen. All right, get on your calculator and see if we can dial this up here. Quickly. 46 squared plus 240 squared minus 2 times 46 times 240 times the cosine of 169 degrees. All right, I'm getting a speed is approximately about 285 miles per hour. So ladies and gentlemen, what's happening here is the wind, there is a component of this wind that is actually acting as a tailwind and actually speeding up the airplane a little bit. So there is a component of this 46 mile per hour wind that is acting as a tailwind to actually speed this aircraft up a little bit. So the aircraft's actual true ground speed will be 285 miles per hour. That's its true ground speed. And to get the heading of that airplane, we would have to find this angle here. But we know side C is 285 miles per hour then. So we could then find this angle here. And once we find this little angle here, ladies and gentlemen, how can we deduce the heading of this aircraft, the new heading from here to here, if we have this little angle here? Well, we know here to here is 273 degrees, so we would just subtract off this angle. We would have the true heading of the aircraft. Okay, so you'd have to find this angle here by using the law of sines and maybe call it angle A. So the sine of angle A is 246 miles per hour, as the sine of the 169 degree angle is to side C, which is 285 miles per hour. And so therefore A is equal to the inverse sine of 46 times the sine of 169 divided by 285. So the inverse sine, 46 times the sine of 169 divided by 285. I'm getting that's about a 2 degree angle. And so, ladies and gentlemen, that's a true 2 degree angle here. So the true heading of the aircraft, the true heading is going to be 273 degrees minus 2 degrees, about 271 degree. That's its true heading due to the wind deflecting it off course. So the wind is deflecting this aircraft off course by about 2 degrees. 271 degrees at 285 miles per hour is the actual movement of that aircraft. Any questions about that problem, ladies and gentlemen?
I like the boat one better.
You like the boat one better, huh? Okay. But do we agree if we go up in an airplane, ladies and gentlemen, I don't know if you've ever seen this before on a windy day, if you're standing on the ground, you ever seen aircraft flying over and the aircraft is pointing, let's say the aircraft is pointing, ladies and gentlemen, kind of like in a northwest direction, but the aircraft is actually moving in this direction because of a strong wind. You ever experienced that before? Where the aircraft has
a
this
landing videos online about airplanes doing that. Actually, I've seen.
Yeah, it actually has its nose pointed in one direction, and yet the movement of the whole aircraft is in a totally different direction because of the wind pushing it, off course. That's what's going on with this problem here. Okay, so this wind is deflecting the path of this aircraft a little bit, not by much, and it's actually aiding in its forward motion. It's adding to its forward speed, because a component of this northeasterly wind is actually acting as a tailwind. Not much of it, but a little bit is, just speeding it up a little bit. Okay. All right. I hope you enjoyed Math 140. Ladies and gentlemen, there is no classwork for this this section. I'm willing to get rid of the Chapter 7 quiz, throw it out. So all you guys got to do is the Chapter 5 and 6 exam, and then bring your questions. I'll put together like a little review for the final exam. And the next 2 days, we'll just kind of mull over what just happened in Math 140 since June 28th, okay? So please bring any questions that you might have tomorrow that have been nagging you throughout the semester, or some weakness that you've been having. I'll be glad to field any of those questions. Or if there are no questions, I'll just follow a review that I come up with. All righty. So, ladies and gentlemen, I hope you have a great day. If there are any other lingering concerns or questions, let me know. Again, I went over with the clock. I keep giving you too much for your money. Sorry about that. You guys have a good day.
Thank you, Mr. O. Have a good day.